Here's another example of a problem from this section. Let's suppose I give you a function. Your book likes to call them t of x here. T of x is equal to, let's see here, 1, 0, 3, negative 3, 1, negative 5, 2, negative 4, negative 9 times the input vector x, y, z. And then the following here is find a vector x such that t of x is this output they give us, which is 6, negative 7, negative 9. And then they say, is x unique? So we can jump straight to the augmented matrix here, as I was mentioning last time. All right, so this is our augmented matrix here. And we do our row operations, and we save time using our calculator here. And so we put that in, and we'll see what we get here. So I'll type all this stuff into the calculator. Hopefully you're all following along and doing the same thing yourself. And we do our row reduction here. And I get the following. And so what this tells us is that since we do have 3 pivots, and there was originally 3 variables, that there's no free variables. And if there's no free variables, that means that there is a unique solution. So it is unique here, and we can read off the answer. X is negative 5, y is negative 3, and z is 1. Or if we want to write it in vector notation, negative 5, negative 3, and 1. So this is the type of question they're going to ask you in this section. And to be honest, there's lots more we could do with this concept. It's just 1.8, doesn't have that much in it. We will see a little bit more in the future, but for 1.8, this is the main kind of idea here. For example, you can look at what is a graphical interpretation of a linear transformation. And it's a little bit easier to see in R2. So let's suppose my function here, as simple as I can be, t of xy is 2x, 2y. What this does is any input vector you have, your output is going to be just twice as long. So that's what this function does. Instead, if you had, say, t from R2 to R2, and your t of xy is yx, then what this does, if you have a point, let's say it is 5, 2, then if you plug it in the function, it's going to be 2, 5. It's going to be this vector here. And if I had a vector that was, I don't know, 6, negative 1, then it would go to this vector here, negative 1, 6. And so what would end up happening in this problem is it's going to be a reflection about y equal to x. Over here, this was a stretching. And you can also have rotations. And I'm actually just going to give you the generic formula here. And it's entirely possible I'm slightly mixing up a minus sign here. But I think it's this here. You can look this up either in the book or online. This is called the rotation matrix right here. And what this does, if you look at it geometrically, is if you have an input vector, then your output is going to be rotated by an angle theta, counterclockwise. So the three main things you can do with linear transformations from a geometric point of view are you can stretch or compress vectors, you can reflect vectors about a line, or you can rotate them, and you can do combinations of these things, but there are some things you simply cannot do. You cannot have a parabola, you cannot have exponential. So linear transformations are very limited, but they're still very useful for a lot of real-world applications. And that'll be the end of section 1.8.